Good morning, grade 8 learners. Welcome back to another episode of Valenzuela Facebook Live Science 8, where learning is fun with Sir JC de Guzman. Before we start, make sure to clean your area of responsibility and have your learning packets with you. So, are you ready? Last week, you were able to explain physical and chemical changes in terms of the arrangement and motion of atoms and molecules, as well as the different phases of matter. Let me see if you can still recall some information on your previous discussion with Sir JP. All you have to do is to determine the phase change in physical changes in matter or the evidence produced in chemical changes in matter. First number. Lira wants to eat an unripe mango, which is color green, but it does not taste sweet. After a few weeks, the mango turns into color yellow and tastes sweet. What type of change in matter happens in the sample statement? And what phase change, if physical, or evidence, if chemical, occurs on the subject? You have 20 seconds to type your answer on the comment section. Your time starts now. Time's up. The ripening of fruits is an example of a chemical change, and the evidence are change in color and taste. Good job, learners! Now that we are able to recall the previous topics, let me share to you our focus on this episode. In this episode, we will determine the number of protons, neutrons, and electrons in a particular atom with a specific topics. An atom is the smallest unit of matter that retains all the chemical properties of an element. Atoms combine to form molecules, which then interact to form solids, liquids, and gases. For example, water is composed of 2 hydrogen atoms and 1 oxygen atom that have combined by a bond to form water molecule. Molecules, on the other hand, refers to a group of atoms bonded together, representing the smallest fundamental unit of a chemical compound that can take part in a chemical reaction. As discussed by Sir JP last week, atom comes from the Greek word atomos, which means uncuttable or cannot be separated into a smaller particle. This idea was stated by Democritus, the student of Leucippus, during 400 BC. For about 2,000 years, around 300 BC, people believed that all things here on earth is made up of 4 elements as per Aristotle. These are the water, earth, air, and fire. But around 1800s, Dalton says that all things are made up of these tiny indivisible particles called atoms. Yes, he is right when he said that everything is made up of atoms. But it was discovered that the atoms can be divided and separated by means of what we call the nuclear fission, which means that the atom is not indivisible. Dalton also theorized that all atoms of an element are identical in mass and their properties. It is true that the atoms are the same when it comes to the number of protons, but does it mean that they are 100% identical? For example, not all the atoms of hydrogen are identical. Most of them does not have neutrons. But there are hydrogen atoms that has 1 or 2 neutrons. That is why we cannot say that all atoms of an element are identical in mass and their properties. Around 1898, Joseph John Thomson showed in his experiment called the plum pudding or bread raisin model that the atom was made of even smaller particles. He is the one who discovered the electrons when he was experimenting with a gas discharge tube. The plum pudding model shows how electrons were distributed within a positively charged sphere, which ended up like this. The plum pudding model had to be abandoned on both theoretical and experimental grounds in favor of the Rutherford's atomic model. Around 1871, Ernest Rutherford conducted an experiment called gold foil experiment, wherein he used a thin sheet of gold and an alpha particle and come up with the result that most particles pass through the foil, while other particles have been deflected as if they had hit something. He then formulates his conclusions, which are: atoms are made up of small positive nucleus. Positive nucleus pushes away the positive particles. The second one, atoms are mostly empty space, which ended up with his nuclear model of the atom that shows a positively charged core called the nucleus and a negative charged electron that orbit around the nucleus. In 1885, Niels Bohr visualized that electrons as rotating in orbits around the nucleus, like orbiting planets around the sun. He theorized that there might be orbits at a different distance from the nucleus, and there should be a specific number of electrons per orbit. In clarification to the idea of Rutherford that the nucleus is a positive core of the atom, James Chadwick says that there is a particle in the nucleus that has no charge or in neutral state, and that leads to the discovery of neutron in 1932. Aside from neutron, which is a neutral charged particle, there are also other particles which comprises an atom. These are protons and electrons. Electrons orbit around the nucleus, wherein protons and neutrons, collectively known as nucleons, are located. Now that you are familiar with their charges and location in an atom, let us now talk about their masses. This table shows you the different masses of each subatomic particles. The atomic number of an atom shows how many protons and electrons present in a specific atom. The neutron, on the other hand, can be computed by subtracting the mass of the atom to its atomic number. These are the following symbols for the subatomic particles: mass number and atomic number. First is Z. Z stands for the atomic number of a particular element. For example, the atomic number of hydrogen is 1, while chlorine is 17. The elements in periodic table were arranged in an increasing atomic number, starting from hydrogen 1 up to organoson 118. On the other hand, A stands for the mass number. The mass number determines how heavy an element is. And lastly, the subatomic particles. The positively charged particle, proton, has a symbol of P positive. The negatively charged particle, electron, has a symbol of E negative. While the neutral charged particle, neutron, has a symbol of N raised to 0. To better understand this, let me show you the different formulas used and how to use it. Always remember that the atomic number of an element is always the same with the number of protons and electrons, and is represented by this formula, wherein Z represents the atomic number, E for electrons, and P for protons. For example, a noble gas helium has the atomic number of 2, meaning to say that this element has 2 protons and electrons in it. Another is for you to be able to get the number of neutron, you subtract the mass number to the atomic number of the atom, and it is represented by this formula, wherein N stands for neutron, A for
the mass number,
and Z for atomic number. For example, chlorine has a mass of 35.45 AMU, and with the atomic number of 17, which means that the number of neutrons present in chlorine is 18.45 AMU. But what if we need to determine the weight of an element? Okay, so for us to be able to get the
mass number,
we just need to add the number of protons and neutrons in an atom, which is represented by this formula, wherein A stands for
mass number,
P for protons and N for neutrons. For example, chlorine has 18.45 neutrons and 17th on the periodic table, which means it has 17 protons. If we add its neutron with the protons, we will get 35.45 as the atomic weight of the chlorine. Now, it's your turn to test your knowledge on what we have discussed. I'll be asking some questions, and what you need to do is to type your answer on the comment section below. Are you ready? Let us start. Can you match the following scientists with their atomic models? Your 30 seconds starts now. Time's up. These are the correct answers. Great job, learners. How about this one? You need to compute for what is being asked or missing on the table. You have 1 minute to answer this question, and your time starts now. Time's up. Now, here is the correct answer. Great job, learners. You are doing great. To sum it up, different scientists leads to the discovery of the different models of an atom and the subatomic particles, which includes the nucleons, a combination of proton, which is a positively charged particle, and neutron, which has a neutral charged particle, and the electron, which is a negatively charged particle. We also use these formulas to get the value of the protons, electrons, neutron, atomic weight, and the atomic number. Okay, so let us now proceed on our question and answer. The question is, if everything is made up of atoms, and atom is made up of subatomic particles, then what makes up the subatomic particles? The answer to that question is that protons and neutrons are made up of quarks. Quark is a type of elementary particle and a fundamental constituent of matter. Quarks combine to form composite particles called hadrons, the most stable of which are protons and neutrons, the components of atomic nuclei and has 6 types, which are up, down, strange, charm, bottom, and top. Leptons, which has also 6 types, namely electron, muon, tau, electron neutrino, muon neutrino, and tau neutrino. And the antimatter particles, which are antiquarks and antileptons, which will be discussed on a higher grade level. So, for more questions related to this topic, you may type it on the comment section or ask your subject teacher during your follow-up discussion. And that's all for today. See you next week. Bonumane!